Hi students, welcome to my lectures on mechanical unit operations. Today we are going to discuss about the pressure drop in a packed bed. Yes, which is one of the typical cases in the industry, and it is frequently encounters in the different subjects of chemical engineering. So let us go and derive how much. Let us say it's a what we are going to do is, imagine a container is filled with a sand. Okay, I have to pump some air from the below. Okay, at what pressure I have to pump the air from the below because of this bed? That is because if I don't know how much pressure drop is happening to inlet and outlet P1 minus P2, I cannot design what kind of pump is required to pump the air from the bottom, because finally I have to set up a pump which can able to pump at certain pressure. Okay, if this is the flow, what should be my pump requirement? That means first of all I should know how much is pressure drop happening from bottom to top. So that is what the today's derivation. Let us start with a very simple one. This, imagine a pipe. Okay, we will start the derivation with this, and suppose you want to pump a water or air from one location to another location, you have to create certain amount of pressure. So P1 is the inlet pressure and P2 is the outlet pressure. The pressure P1 will be higher than the pressure P2, then only the flow is going to happen. Because the P1 is higher, if I connect a manometer at these two locations, you can see the manometer, if this is a mercury, imagine what happens. The level of the mercury will come down compared to the level of the mercury here, because of the high pressure, because the mercury will come down the manometer compared to the pressure here. That is why you get some certain pressure drop. So for these things we can easily measure P1 minus P2 for this length L. So that is what the pressure drop, delta P by L. P1 minus P2 divided by L, that is nothing but my pressure drop per unit length. Okay. For the pipe, there are simple equations available. For the packed bed, for the same conditions, now the container is filled with some sand or any other particles. P1 is the inlet pressure and P2 is the outlet pressure. The difference between P1 and P2 is called delta P in this length L. So you can compare the pipe and the packed bed over here. Okay, let us see. For laminar kind of conditions, okay, and you can measure the pressure drop using Hagen-Poiseuille equation. Okay, Hagen-Poiseuille equation, which is delta P by L, that is pressure drop within this length L, can be estimated using Hagen-Poiseuille equation. The Hagen-Poiseuille equation is 32 V mu by d square. Okay, 32 u0 mu by d square. What is V0? Is a velocity. What is how much velocity the air is going inside, and mu is the viscosity inside the fluid, and d is the diameter of the pipe, L is the length of the pipe. So if you know velocity, viscosity and diameter, you can estimate delta P by L. That means how much pressure drop is happening within this length L. We use the same equation for the packed bed also by making some small changes. Let us go. That means once you know this, you can able to measure the pressure drop. Imagine this is the actual bed for which we wanted to measure the delta P, which is not very simple, which is here you can know the diameter. What diameter? Pipe diameter. Here you cannot take this packed bed, I mean this particular diameter. Why? Because here the flow is happening over entire diameter. Here you can see only small spaces are available, okay, between the particles. So in such cases you cannot take the entire diameter for the flow. Only few, there are spaces, through these spaces the air or water will move through the bed. So the same equation, it cannot be directly used because the velocity inside the bed is different, the diameter available for the flow is different. Okay, as I know in the previous lectures, I have defined how the superficial velocity is measured. The velocity inside the bed is nothing but the empty tower velocity divided by epsilon porosity, because here this V0 only, that means velocity of the flow here V0 divided by epsilon, that is what the velocity of the fluid inside this bed. That's what the first change you are supposed to take, because velocity in the pipe is different, velocity inside the bed is different. V0 is the superficial velocity. D equivalent diameter, okay, that's what we have to find out. What is the diameter of this particular bed, okay, which is typical. Let us, we will going to derive on this basis, and D equivalent is nothing but what could be the equivalent diameter of this bed. What diameter of the bed I have to use to measure the pressure drop. Hence here I can measure the diameter directly here, because not entire diameter is available for the flow. Only there are certain spaces through which the flow has to take place. So let us, because there is no direct available thing that can be able to measure diameter, what people have done is, let us make one hypothetical, packed bed here. Okay, here the diameters length are the same, here also diameter and length is the same. What we have done is, because we cannot directly measure the diameter over here, what we did is arrange the particle in certain fashion. Okay, here the particles are random, here the particles are arranged in specific straight lines. In between these particles there are channels that are available. Okay, you cannot randomly, because the dimensions should be the same. What dimensions? The particles, if you count the particle surface area here and the particle surface area here, should be the same in the hypothetical bed, and spaces between the particles is nothing but void spaces. The quantity of void spaces in the actual bed should be equal to the quantity of the void spaces in the hypothetical bed, because finally we have to measure the equivalent diameter. To do that, this is the procedure. So suppose if I arrange the particle in certain fashion, I have some diameter, D equivalent diameter, and such channels are there, 1, 2, 3, 4, 5, up to n channels. There is no specific diameter as such. Let us divide, there are n channels that are available here in this hypothetical bed, in which I have to calculate the D equivalent diameter. So diameter of one such a channel is called the DEQ. If you have n channels, that means n empty straight channels are there, cylindrical channels, one of the channels diameter is the D equivalent. Maybe you can ask, sir, we are supposed to count all these channels, right? Why we are taking only one channel diameter? Because later on we relax this assumption by conducting the experiments and find out the actual equation. So let us go by this way. One of the channels diameters D equivalent, which are supposed to use in this particular equation. To find out D equivalent diameter, I have to follow 3 steps. Okay, this is your actual, this is your hypothetical bed, and to derive D equivalent I have 3 steps. Step 1, step 2, step 3. In step 1, equate the surface area. That means the surface area of these particles should be equal to the surface area of these particular particles in this hypothetical bed. If you equate these two, you get one equation. Second, step 2, equate void volume. The empty spaces available between the particles, the empty spaces of this particular n channels, if you equate these two, okay, you get one more equation. And the third step is, by equation 1 and equation 2, by equating surface areas as well as void fractions, I get final equation from which I can able to derive D equivalent. So let us go to step number 1. What is the step number 1? Equate surface areas of the particles. Okay, step number 1. Actual bed surface area is equal to the hypothetical bed surface area. So this is how I can able to measure the SP by Vp is nothing but surface area to volume ratio of one particle. Okay, surface to volume ratio. Okay, into volume. What is the total surface area available here? Because I have to count the particle surface area here. Every particles, I have to count down all the surface area for all the particles in this particular volume. Okay, that is why surface to ratio of one particle into volume will give you total surface area. That means you can see surface area by volume into total volume will give you total surface area of the particles in this particular volume. But imagine, not every space is occupied with the particles. There are empty spaces also. In empty spaces there is no surface area. So to remove this empty space, I have to multiply with one more factor which is called 1 minus epsilon. Epsilon is the porosity, empty spaces porosity. What is 1 minus epsilon? The one which is not porous, one is not porous. Epsilon is how much of empty spaces, 1 minus epsilon is fraction which is occupied by the particles. So surface to volume ratio into total volume, this volume that cancels out, you get a meter square, total surface area into volume, the meter cancels, total surface area into fraction of non-porous volume which is called 1 minus epsilon. You get actual bed surface area, how much surface area is available in the bed. Similarly, how much surface area is available in this particular hypothetical bed is nothing but, I know this is the cylindrical channel. What is the surface area of the cylinder? Okay, 2 pi r into length. That will get me circumferential surface area of the cylinder. How many cylinders I have? N cylinders, let us assume. N channels, cylinders or channels, N channels, circular cylindrical channels. The surface area of actual bed is equal to the total surface area of the channels, N channels, N into pi d equivalent into length. So if you equate these two, what is the volume? Volume is nothing, what is the volume of the cylinder? Surface area into length. S0 is the surface area of this cross sectional surface area, okay, available for the flow. So V is nothing but S0 into L. Substitute in this equation, you get SB by Vp. You know all this sphericity formula, right? Surface to volume ratio of the particle is nothing but 6 by phi s into dp. Phi s is the sphericity, dp is the diameter of the particles inside, okay. Once you substitute equation number 4 in the equation number 5 and equation number 3 and do the substitutions and rearranging, you get this equation number 6. Okay, this is the first step, you get one equation. Let us see what happens to the second equation. Second step, I have to equate void volume. That means the empty spaces available here in this actual bed should be equal to the empty spaces available in the hypothetical bed. So if I equate these two, then I get void volume in the bed is equal to void volume of all the channels here, okay. And let us go to the other side of the board. In the second step, V, total volume into porosity. That means if I equate void volume in the actual bed, what happens? The total volume multiplied by porosity. That will give you void volume in the bed, actual bed. Similarly, what is the void volume in the hypothetical bed? It is nothing but channels, channel volume, N into and volume of one channel, okay, d pi d equivalent square by 4, okay. What is the volume? It is surface area into length. If you, because you get this equation number 7, now you substitute equation number 7 in equation number 6, okay. If you substitute and rearrange, you get this is the equivalent diameter of any channel, okay. Once you know the equivalent channel, substitute in the equation number 2, okay, you get the final equation. This is the equation that is used to measure the pressure drop in a bed, okay. Not straightforward, we have to do some changes. Just like a Hagen-Poiseuille equation used to measure the pressure drop in the pipe, this is the equation used to measure the pressure drop in a packed bed. As I told you, I have taken only one single channel, right, which is not appropriate. I have to consider all the channels available in the hypothetical bed. But people have done some experiments. We cannot straightforward use this equation. They have to conduct different experiments, okay. They use different velocities, different viscosities of the liquid, different sphericities and different diameter of the particles. By conducting the different experiments, they have found out this equation straight away forward cannot be used. Instead of that, you have to use this kind of semi-empirical equations. Semi-empirical equations means these kind of equations come based on the fundamentals as well as the experiments. If people will club fundamental equations as well as the experimental results, that comes under the semi-empirical equations, okay. Empirical equation means completely based on experiments. Fundamental equations means completely based on the fundamental concepts. Semi-empirical means few equations that comes from the fundamentals, which is clarified with the experimental results. Okay, these kind of the semi-empirical equations are used. Okay, the first equation is proposed by Kozny-Kármán equation, which is applicable when the bed Reynolds number is less than 10. Okay, mainly for laminar or wherever the viscous forces dominates inside the bed, you have to go for the Kozny-Kármán equation. One such equation is valid when the moment the bed Reynolds number is less than 10. And the other equation proposed by Burke-Plummer equation, this is mainly valid for the turbulent kind of conditions where pressure drop is mainly because of the kinetic losses. Okay, and this is when bed Reynolds number is greater than 1000, use this particular equation in measuring the pressure drop in a packed bed. The third one, the Argon equation, very famous equation. When you have this condition used for both the laminar as well as the turbulent. For general cases, you have to use for the Argon equation, which consider kinetic losses as well as the viscous losses. I hope now this is the basis. This equation is the basis for getting this kind of equations, because if you don't get that, what are the parameters that affect the pressure? Here you can see based on some assumptions, people have come up with some equations, because pressure drop is affected by velocity of the flow and viscosity of the flow, porosity of the flow, sphericity of the flow, diameter of the particles. These many parameters thus affect the pressure drop in a packed bed. So let us use these equation in estimating a pressure, how much pressure. Let us take an example. Let us take a container filled with sand or any other particles. Let us start pumping the air from the bottom. To pump air from the bottom to certain velocity, how much pressure I need at the bottom. Okay, let us do that example so it will be more clear. Yeah, this is the example we are trying to solve, because there is a bed of particles is there in the container. I have to pass some air from the bottom at certain pressure P1. The other end is open to the atmosphere. That means the air that comes out is at a 1 atmosphere. I have to estimate, because what pressure I have to use at the bottom so that I get required flow rate at the top. Okay, that is why it is important to measure the pressure drop in a container. Given the diameter, because they have given what is the diameter, okay, of the container, what is the height of the packed bed, what is diameter of the packed bed, what is the particle diameter dp, and they have given what is the viscosity and what is the porosity, that is what is the empty spaces inside the things, what is the length, what is diameter, what is the density, mass flow rate. That means I have to pump the air from the bottom around 60 kg per minute. Okay, given these conditions, what is the P1 that I have to require, okay, so that I can get this much of flow rate at the exit, which is open to atmosphere, which is at P2 is at 1 atmosphere. Okay, let us go a step by step. First of all, I have to calculate the volumetric flow rate. Okay, volumetric flow rate Q is given by the mass flow rate divided by density. Mass flow rate given 1 kg per second. Okay, the density of the fluid 1.156 kg per meter cube. Okay, from this I measured 0.865 meter cube per second, which is the volumetric flow rate of the air. That means I have to pump the air at this certain flow rate. What is the velocity? That means empty tower velocity. I have already discussed about the empty tower velocity. That means empty tower velocity is the velocity if I remove the bed. Okay, now the tower is empty. At that conditions, what is my velocity of the bed? That is called the empty tower velocity. So velocity is nothing but flow rate divided by area. Okay, the flow rate I have calculated 0.865, and the area available for the entire flow is this, is the entire area available for the flow. Then only I can get empty tower velocity. I have to take all the area available for the flow. If I do that, I got the empty tower velocity is 0.705 meters per second. Okay, this is the empty tower velocity. And I have to find out which equation I am supposed to use now. Kozny-Kármán, Burke-Plummer and Argon equation. To do that, you have to find out the Reynolds number. That is a bed Reynolds number. The bed Reynolds number is dp, and this superficial velocity v0, density divided by mu divided into 1 minus epsilon. I have given all the given every other parameter value. We have found out this Reynolds number bed is 903. It is, because if it is less than 10, use for the Kozny-Kármán, greater than 1000, you go for the Burke-Plummer. If it is in between these two, it will cover the entire range, right? Better you go for the Argon equation. So because my Reynolds number is 903, I go for use Argon equation. If I substitute, equation number 12 is the Argon equation. If I substitute all the values, I get delta P, that is P1 minus P2. P1 minus P2 is 2477.5 Newton per meter square or Pascal. Delta P is equal to P1 minus P2 is this much. P1, that means the one pressure at the bottom is nothing but 2477 plus the pressure at the top. I know the pressure at the top, P2 is at open to atmosphere, this is 1 atmosphere, 101325 Newton per meter square. So P1 is equal to 2477.5 into plus 101325 is equal to 103802 Pascal. Okay. This much Pascal, how much atmosphere? 1.024. That means the P1 should be, for this particular flow rate, 60 kg per minute, for this much amount of bed having this much porosity, length, diameter, I have to give at least minimum pressure at the bottom is 1.024 atmospheres. Okay, so that I can maintain this flow conditions. So this is what the use. This has a multiple uses. I can students, if you are good at this, these kind of equations that will come in each and every subject, whether you take the CRE, mass transfer, heat transfer, wherever the packed bed, because in all industries people use the packed bed mainly. So this kind of knowledge is very much essential. Okay, I hope you have learned good. I'll come up with the new. Thank you very much.